Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's Scribblecast, where you can download organic chemistry lectures for your study and perusal. In today's lecture, we're going to continue revisiting hybridization and labeled orbital diagrams. Last lecture, we learned about the basic hybridizations available to carbon. We learned about the sp cubed hybridization, sp squared, and sp hybridizations. We learned how to draw the shapes of these hybridizations, and we learned how to produce labeled orbital diagrams that contained these versions of hybridization on carbon. What we're going to do is add to this and consider the relative orbital sizes and then examine hybridizations of these type in atoms that are not carbon. Now, what's interesting is in terms of relative orbital size, we can rank these orbitals in terms of percentage S character, all right? If you like, percentage S character. Now, if we do this, we can attribute each letter to an orbital. That is, the sp cubed was made by mixing S with a P and a P and another P. In other words, we mixed 4 orbitals. So out of 4 orbitals, S made up 1 orbital. Or we had 25% S character. When we had sp squared, we had 3 orbitals, one of which is a S. That's 33% S character. And when we have hybridization of sp, S is 1 orbital, P is the other orbital that was mixed. S is half or 50% of the character of that orbital. Now, what conclusion can be reached from this is one of size. S orbitals tend to be smaller and less diffuse than p orbitals of the same shell. So if we're comparing a 2s with a 2p. The more S character you have, the smaller the orbital size. So if we remember that the sp, sp squared, and sp cubes were all basically the same shape, and I will exaggerate this, of course. Remembering plus, minus are not charges, but represent phase. Because of greater S character, the sp orbital is actually smaller and less diffuse than the sp squared, who's likewise a little smaller and less diffuse than the sp cubed. So in terms of S character, sp orbitals are smaller than sp squared, who are smaller than sp cubed. The result of this is that if you compare a sigma sp sp bond, say to a sigma sp squared sp squared, the sigma sp squared bonds are going to be longer than the sigma sp sp. Shorter bonds also typically represent stronger bonds. Right? So since sp sp is shorter than sp squared is shorter than sp cubed, we get more of a concentration of electron density in less space. So sp is the stronger bond. Having established this, what we want to do now is move on and try to apply this hybridization approach to atoms other than carbon. And let's begin with a molecule such as ammonia. Now, last lecture we defined a term H.O.N, hybrid orbital number, sometimes called S.N, steric number, sometimes called C.N, coordination number. And the hybridization orbital number was explained to you as the total number of atoms, okay, approaching the central atom. So you count up the atoms bonded to the central atom, and that would give you a hybrid orbital number. And from that, you could get hybridization. For atoms other than carbon, in fact, for certain carbon molecules, we have to add one new aspect to our definition of H.O.N. H.O.N is not just the number of atoms. H.O.N, hybrid orbital number, S.N, steric number, or sometimes it's called C.N, coordination number. We defined it as the total number of atoms bound to the central atom. We don't count bonds, we counted atoms. But in actual fact, it is the sum of the atoms and lone pairs. Now, the examples we used yesterday had no lone pairs, so we didn't need to include that. But we're going to start putting on lone pairs, so we're going to need to do this. To figure out hybridization, right, we're going to have to add the atoms in lone pairs around the central atom. And when you get an H.O.N of 4, remember that's sp cubed. H.O.N of 3 is sp squared, and H.O.N of 2 is sp. So we're going to try this on a first molecule, NH3. Now, this automatically becomes a trick question. If you're asked to draw a labeled orbital diagram for a molecule like NH3, the first thing you must always do is check the Lewis structure. Why? Because when someone writes down a molecular formula for you to produce a labeled orbital diagram, they may or may not be showing the lone pairs. And the only way you can figure out the lone pairs is by actually doing the Lewis structure. Remember, to do a Lewis structure, you must calculate the total number of valence electrons. So our total number of valence electrons. Nitrogen has how many valence electrons? Nitrogen has 5. And then we got 3 times, how many valence electrons for hydrogen? 1. 3 times 1. And so we get 8 valence electrons. So it looks like this is going to be a pretty easy Lewis structure. We have our nitrogen. We got 1, 2, 3, 4, 5. We have hydrogen, hydrogen, hydrogen. And I can join them up. If I link them up, nitrogen ends up with 8. Hydrogen has its 2 electrons it needs, and I end up with this as my Lewis structure. And notice there is a lone pair. All right. So when I'm going to calculate hybrid orbital number, if I had originally done the hybrid orbital number without the lone pair, I would have said 3 atoms. I would have come up with sp squared, and I would have gotten the wrong answer. The truth is, NH3 has a lone pair. And when you calculate hybrid orbital number, you must count the atoms and the lone pair. 3 atoms, 1 lone pair. Hybrid orbital number 4. The nitrogen is sp cubed. This allows me now to draw my nitrogen in a labeled orbital diagram by drawing the sp cubed shape. Okay? I can put in my H's. And I can put in my electrons. Now nitrogen, I put one electron, all my electrons around the nitrogen. But nitrogen had how many valence electrons? It had 5. So one of them is a lone pair. Okay, there's the 5 electrons. Notice I put the 3 up pointing the same way. Hydrogen has its electrons. I'm making pointing down. And I put in all the electrons. Now I can provide bond angle. And I'm going to give you the correct solution right now and then tell you what we're going to do. In Chem 201, or your general chemistry course, you are going to discover that lone pair bonding pair repulsions are greater than bonding pair repulsions. And what that means is this angle gets squeezed by the lone pair. Now, the typical bond angle for sp cubed was 109.5. In your general chemistry course, you would have to mark this as less than 109.5. But for my course, I'm not really going to press this matter. And so I will accept 109.5 degrees here, even though we know it's slightly less. Okay? So the bond angle is 109.5 degrees. Now the shape of the nitrogen is tetrahedral, if you count the lone pair. Now, usually shapes target positions of atoms, and since there's no atom on the other side of the lone pair is often ignored. So the shape in this case would look like a trigonal pyramid, and is called trigonal pyramidal. And this is what you would give as the shape in a general chemistry course. Again, we're not pursuing hybridization as far as you're going to take it in general chemistry. We're going to only use it insofar as we need to use it in organic chemistry. So I will again accept a shape as tetrahedral. Just remember that this shape we're giving includes the lone pairs and is not the true shape of the atoms, ignoring the lone pair. And lastly, we need to label the bonds. Nitrogen is using an sp cubed orbital. Hydrogen is using a 1s. So what we have here is a sigma 1s sp cubed. We don't label the lone pair, and we can indicate nitrogen is sp cubed hybridized. So you can determine the hybridization for atoms other than carbon. And notice that what we do here is complicated by the fact that we have to draw the Lewis structure in order to make sure we've got the lone pairs. Let's look at a labeled orbital diagram example of this so that you might be better able to determine what's going on and how to do a labeled orbital diagram. So let's try an example here. And what we're going to look at is, suppose you were asked to draw the labeled orbital diagram for CH3. CN. If I was asked to draw this labeled orbital diagram for this molecule, the first thing I must do is check the Lewis structure to search for lone pairs. And don't make the mistake of thinking carbon can never have lone pairs. Carbon usually doesn't, but it can have lone pairs when the carbon is charged. So you do have to be careful. So let's begin with the Lewis structure by calculating the total number of valence electrons. Our total number of valence electrons, we have 3 hydrogens, so 3 times 1. Hydrogen has 1 valence electron. We have 2 carbons plus 2 times how many valence electrons in carbon? Carbon has 4 valence electrons. And we have nitrogen, which has 5 valence electrons. So if I look at this, I've got 3. 2 times 4 is 8. Plus 3 is 11. 16 electrons. So if I draw a carbon with 4, my hydrogens have 1. Hydrogen has 1. Hydrogen has 1. Carbon has 4. Nitrogen has 5. We can start joining things up. Hydrogens want 2 electrons to complete its shell. The 1s, there's no such thing as a 1p, so it only needs 2 electrons. Carbon wants 8, 2, 4, 6, 7. We join up here, we've got 8. That carbon's happy. 2, 4, 6. 2, 4, 6, 7. 2, 4, 6, 8. 2, 4, 6, 8. And notice there's a lone pair. So we can draw our Lewis structure. And always double check your Lewis structure to make sure you've got the right number of valence electrons. There we go. 2, 4, 6, 8, 10, 12, 14, 16. Check. We have 16 valence electrons. If I was doing a full Lewis structure and I was asked to calculate formal charge, I could now check the formal charge of every atom. Now what I want to do is go back to my model and notice we were missing a lone pair and we had a triple bond here. We're missing the lone pair and we want to make a labeled orbital diagram of this. So this is really what we need to be able to draw the labeled orbital diagram. We need that lone pair. Now we can calculate hybrid orbital number. If I do it for this carbon, right? Okay. In fact, I could label this carbon alpha, this carbon beta. H.O.N. For carbon alpha is 4 atoms, which means it's sp cubed. H.O.N. for carbon beta equals what? Well, we've got a carbon atom attached to it and a nitrogen. It's 2. Notice I didn't count bonds. I counted atoms. There's a carbon and a nitrogen attached to it, so it's sp. And lastly, H.O.N. nitrogen, hybrid orbital number for my nitrogen equals what? Nitrogen has a carbon attached to it, 1, and a lone pair, 1 plus 1 is 2. It's also sp. So we're ready now to begin building a labeled orbital diagram, and we can erase this. We can go right back to our original question, CH3, but now we know it's C triple bond N with a lone pair, and we know this guy is sp cubed, this guy's sp, and the nitrogen's sp. And using that, now all I have to do is take the shapes I memorized and begin drawing them. And we can do this. So I'm going to begin with a nitrogen, and I'm going to draw an sp shape. Right? And sp, remember, are linear in relationship. So here's an sp orbital, and on the other side is a second sp orbital. They get as far apart as possible. Then I'm going to draw 1, 2p. And I'll draw the 2p coming out at you on an angle. And notice I don't make it look like a butterfly. Straight up and down, and one on a diagonal. Now I can do the carbon. and I can give it, this carbon has its also sp, so here's its sp overlapping with nitrogen's sp, and I'll make its other sp over here. Because it's sp hybridized, it also gets a 2p. And a green 2p coming out of the paper, which I draw on the diagonal. Great. Now I can go back, draw my carbon. This one's sp cubed, so I can draw its sp cubed pattern. It's on its side, so I draw its lobes up here. And of course, they're not that nice. I'm a bit sloppy here. And I can put in my H's. And I'm ready to add my electrons. I could start anywhere, okay? Let's start with the carbon in the middle, for example. Well, carbon has how many valence electrons? 4. I put 1 electron in an sp, 1 electron in a 2p. Well, both red lobes are a single 2p, so they only get 1 electron. You could put the electron in the bottom lobe, top lobe, it doesn't matter. Notice I'm making them all the same spin. 1 electron in the green 2p. This black orbital that's empty is a separate sp. That's why I can put an electron in it. There are the 4 electrons for carbon. Nitrogen have 5 valence electrons, but since this carbon is bound to nitrogen, I'm going to make them down. And then I'm going to make the other electrons down in the 2p's. There's 3. So this guy must be the lone pair. The sp on the other side must be holding the lone pair. Now, since we do have some side-to-side overlap, you usually draw it. I'm going to link up the red 2p's because they're touching each other side to side. And then I'll link up the green 2p's because they're touching side to side. Okay. And now I can put in the electrons for the sp cubed carbon. This one's up, so according to the Pauli exclusion principle, there must be opposite spin, so he's down, so I put the rest of the 4 electrons also down, making sure they're the same spin. And then I can add hydrogens 1 electron up and keep everything balanced. Now I've done my labeled orbital diagram. Wunderbar. Here we are. Excellent. Now I just have to label. I've got my electrons. I need to show bond angles. So, we can mark some bond angles. Let's do this. Here's a bond angle around an sp cubed carbon. What is the bond angle in sp cubed carbon? It's 109.5 degrees. What is, say, let's try this bond angle. What's that bond angle? Is it 90 degrees? No. That's right. I'm tricking you. A bond angle must be measured from a bond, like a carbon-carbon bond, to another bond, like the carbon-nitrogen bond. This is the angle. What is that bond angle? Well, that bond angle obviously is 180 degrees, and for sp it's linear. What about this bond angle? Well, nitrogen's sp, so this bond angle is also 180 degrees, right? Wrong. What is this? Is this a bond? Do you see an atom here? No, you don't. There's no atom here. X does not mark an atom, so this is not a bond. What is it? It's a lone pair. What is a lone pair called? It's called a non-bonding pair of electrons. Bond angles are not measured from bonds to non-bonds. There's no angle there. So those are my 2 bond angles, and they're the only ones in the molecule. I've already marked the hybridizations. I put in the electrons. So all that's left now is to label the bonds. Let's start here. What is this guy? Those three guys are a head-on collision between the 1s of hydrogen and what's the hybridization of carbon? sp cubed. What about that bond? Well, it's a bond between two carbons. This carbon's sp cubed, this carbon's sp. So it's a head-on collision between the sp cubed of one carbon and the sp orbital of another carbon. You're beginning to get the idea. What about the bond here? Well, this carbon has an sp orbital, this nitrogen has an sp, so it is a head-on collision sigma sp sp. And that just leaves our green pi overlap orbitals and our red ones. They are side-to-side overlaps, so they're pi, and they are 2p orbitals, overlapping with 2p. And there you have a labeled orbital diagram for the molecule acetonitrile. Notice, though, to do this, you had to do the Lewis structure first to discover if there was a lone pair. Okay, now we can look at some other functional groups of molecules and check out their hybridizations. For example, what is the hybridization of oxygen and water? Well, if I gave you just H2O, you could do its Lewis structure and you would very quickly discover there are two lone pairs on the oxygen. And you can try that at home. Try doing the Lewis structure. And if I calculate the H.O.N for oxygen, then I have two atoms plus two lone pairs, 4. The oxygen is sp cubed. Now the shape for sp cubed, of course, is tetrahedral. In this case, though, if you didn't count the lone pairs, you would report the shape as bent or V-shaped. But for this course, it's sufficient to give the shape, including the lone pairs. Likewise, molecules that are alcohols replace an H with an organic group, like a CH3. And so an alcohol is just like water. And its oxygen's also sp cubed hybridized. We can run into examples where oxygen is off of a double bond. Now, a molecule like this would be the molecule acetone. Now, if this molecule was given to you like this, draw the Lewis structure. It is tricky. Why do I have to draw the Lewis structure? Well, let's try it. The total number of valence electrons in this system is 3 carbons, each has 4 valence electrons, 6 hydrogens, each has 1 electron, and oxygen, who has a 6. So what's that give me? Well, we've got 6 times 1 plus 3 times 4 plus 6, 12, 18, 24 electrons. So if I start assembling this, oxygen has 6, carbon has 4, carbon has 4, carbon has 4, and then I've got my hydrogens. 1, 1, 1. And if we start linking up, this carbon has 2, 4, 6, 7. I can link him up. Now he's happy with 8. And likewise, this carbon is 2, 4, 6, 7. Link him up. He's got 8. Now, this carbon has 2, 4, 6. If I link up with 1, I get 7. If I link up again, I get 8. So, now he's happy. Oxygen has 2, 4, 6, 8. Everyone's happy. And if I draw the Lewis structure, you notice the oxygen has 2 lone pairs. Double bond. C, C, H, 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 C, H, H, H. So the only difference to this is the oxygen has 2 lone pairs. So if you were to be calculating the hybridization of all the carbons in the oxygens, well, this carbon has 3 hydrogens and a carbon attached to it. So there's 4 atoms, so he's sp cubed. This guy's also sp cubed. This carbon has an oxygen and 2 carbons, it's 3, so he's sp squared. And what's oxygen got? It's got the carbon, and then it's got 2 lone pairs, so oxygen's sp squared. Remember, the hybridization tells you what shape to draw. If you didn't know there were lone pairs, you would never have guessed that the oxygen's sp squared. Okay. I stated it last lecture, and I'm going to restate it again. What are the advantages of hybridization? What are the advantages of hybridization? Hybrid orbitals give you better orbital overlap. Hybrid orbitals give you better orbital overlap. The electron density is concentrated between the bonds. It's more directed. If you compare it versus, here is an s orbital. Here is, say, a 2p. When you mix the s and the 2p, you direct more of the lobe in the direction of the bond. And this leads to better orbital overlap because there's more orbital available in the direction of the other atom you're going to bond with. And the second advantage is VSEPR, valence shell, electron pair, repulsion theory. And VSEPR basically states that these orbitals get as far apart as possible. And hybridization allows this. By hybridizing, you get orbitals that can achieve a VSEPR geometry that can minimize repulsion. So hybridization allows minimization of bonding pair repulsion. So, VSEPR allows minimization of bonding pair repulsion. These are 2 major advantages of hybridization. Now that we've learned about hybridization, we can begin to revisit a concept that we covered in the last few lectures, and that is molecular dipoles. And the reason we're going to revisit this is because molecular dipoles, if you remember, were important because they allowed us to know something about the shape of a molecule. And since hybridization gives us shape, hybridization will allow us to make certain predictions about a molecule's dipole moment. Suppose I gave the following question. Suppose I stated, rank the following molecules in increasing dipole moment. And then I added the statement, be sure to show all your work. Show all your work. Okay. So rank the following molecules in increasing dipole moment and show all your work. And suppose I gave you the molecule BF3. And I gave you the molecule NH3. And the molecule... let's try NCl3. Let's try those. How would you begin? This is really a loaded question. In order to determine the dipole moment of this molecule, I must know its shape. I must know all of these molecules' shapes before I can put in the dipoles and add the vectors. Before I can know shape, I must know the hybridization. Before I can know hybridization, I must know if any of these molecules, central atoms, have lone pairs. And to get lone pairs, that means I have to do the Lewis structure. So this really is a tricky question. It's loaded because saying show all your work means I've got to find the Lewis structures, build up the structure, figure out the hybridization, put in the dipoles, add the vectors, and see what happens for each. So we've got BF3, NH3, NCl3. Let's begin and do this. Start with BF3. Now, we may not have covered it in the Lewis section of these notes, but BF3 is a special case. Boron and aluminum are one of the rare molecules that can form stable molecules without 8 electrons around them. And we're going to actually look at that in this case. Total number of valence electrons. So let's put that in. Total number of valence electrons. And boron, if we look it up in the periodic table, has 3 valence electrons. Fluorine has 7, so we have 3 times 7. 3 times 7 is 21, plus 3 is 24 electrons. So I'm going to take a boron, give it its 3, and then I'm going to put fluorines out there with 7 electrons. There's a fluorine. Here's a fluorine. And here's a fluorine. And I'm going to join these up. Now, normally I would go for 8 electrons. I would dump in a lone pair to make a double bond and get 8 electrons around boron. What's interesting is halogens typically, fluorine, bromine, chlorine, are terminal, monovalent, and they don't like making multiple bonds. The second thing, boron and aluminum can form stable 6-electron molecules. And these stable 6-electron molecules will have an empty orbital, which can react. Because they have an empty orbital, they're a Lewis acid, but they are stable. And so, here is our BF3. Now we're going to focus only on the dipole on the central atom. The fluorines, lone pairs, effectively produce small dipoles that slightly cancel each other. Who's more electronegative, boron or fluorine? Well, before I answer that question, before I actually determine dipoles, I have to know the shape of the molecule. And to get that shape, I must look at the boron and figure out its hybrid orbital number. What is the H.O.N of boron? The H.O.N of the boron is 1, 2, 3, 3 atoms plus 0 lone pairs. So H.O.N is 3, which means the boron is sp squared. What is the shape of sp squared? Remember, it was trigonal planar. That means all 3 bonds from the boron point to the corners of a triangle. Trigonal planar. Okay. Now, let's put in our dipoles. A boron, a fluorine. Who's more electronegative? Fluorine's more electronegative. So the arrow points to fluorine. Now, let's look at another. Boron, fluorine. It's the exact same dipole. Same length, same strength, just pointing a different way. And this boron, fluorine is pointing that way. So what you have is a tug-of-war vectors. Now, let me ask you a question. If you drew a perfect triangle, and of course I can't draw a perfect triangle, but I shall try. Oh man, that's terrible. A little better. And you stood somewhere in the middle, and one person was pulling with a rope up that way, one person was pulling with the rope that way, one person was pulling the rope that way, and it was equilateral, and all the ropes were same length and pulling the same strength. Which direction would this guy move? Well, the person pulling up and pulling here, here, and here, and here, all pulling with the same force, the guy doesn't move. These 3 vectors pointing to the corner of a triangle cancel each other. If 3 vectors add up head to tail with the same length, the same strength, they all end up going back to the exact same place. You don't have to understand vector condition if you think about it as a tug of war, but essentially BF3, because it's trigonal planar, all the vectors are pulling equal opposite directions. The dipole here, adding all those dipoles together, will give you a dipole moment that is equal to 0. Now, you have to do the same thing for the other 2 molecules. Let's do NH3. NH3 has total number of valence electrons. Equal, didn't we just do this? 5 plus 3 times 1 equals 8. I can give nitrogen, it's 5. Hydrogen, hydrogen, hydrogen. Give them the 1. We did this already, I'm sure of it. So here's my Lewis structure. And lo and behold, nitrogen has a lone pair. The hybrid orbital number for nitrogen, or nitrogen, equals 3 atoms plus 1 lone pair equals 4. So it's sp cubed. That means sp cubed. Nitrogen is sp cubed, which means it's tetrahedral in shape. Now here's where things get interesting. If I draw my nitrogen with a lone pair, this is a lone pair, who's more electronegative? Nitrogen or hydrogen? Well, nitrogen is. So the dipole is going to point up towards nitrogen. And those 3 dipoles are all pointing towards nitrogen. Those 3 dipoles are going to add together to produce a small dipole pointing up. Now what's interesting is lone pairs also have a dipole pointing away from the nucleus. So this dipole, these 2 dipoles are going to add together and produce a mu equal in that direction. And it's going to be pretty big because it's going to have the dipole strength of the lone pair and the dipoles that are pointing towards the nitrogen adding in with the dipole of the lone pair. So far we see that NH3 is going to have a bigger dipole moment, a bigger mu than BF3, which has a mu of 0. Okay, why don't we try now? Let's try NCl3. Well, NCl3 is exactly the same as NH3, but you still should show all your work and calculation for it, okay? So I would show all my work, and I should have for NH3 written down the shape. Remember the shape without the lone pairs, trigonal pyramidal. It's like a trigonal pyramid. But with the lone pair, it's just tetrahedral. Okay, so we'll leave the mu value, we'll leave this, and we've got this. So we're starting with NCl3. Total number of valence electrons is 5 for nitrogen, 7 for chlorine, 3 times 7 is 21, 28. Ooh. 28. So if I'm building this, I can put in my 5 electrons around nitrogen. My chlorines have 7. Chlorine has 7. Chlorine has 7. If we join these up, we see NCl3 is just like NH3. The only difference being, let's make some more room. The only difference being, so we can see this, so I'm going to rub this out and make the final drawing. I would have left this in if I was showing work. I'm just running out of room here. So if I join that all up, what I end up with is something like this. Now, let's discuss the differences for this. Now, what is the hybridization of nitrogen in this case? Well, in this case, it's exactly the same as NH3. The hybridization of nitrogen has 3 atoms plus 1 lone pair. So it's 4. So the result we get is sp cubed. The difference here, though, of course, is it's a little more complicated because each of these Cl has lone pairs, and these lone pairs are pointed out in a way. It turns out that the lone pairs do have a small effect on the dipole, but we're going to ignore it. As I said before, we're going to focus on the dipole moment around the nitrogen and use that. So who's more electronegative? Nitrogen and chlorine. If nitrogen's more electronegative, the dipole will point this way. If chlorine's more electronegative, the dipole will point to chlorine. Do you remember? Did you pick nitrogen? Did you pick chlorine? Well, guess what? They're approximately the same. So there's no dipole between the NCl bonds. There's only the dipole due to the lone pair. Now let's compare this to what happened in NH3. NH3 had the same dipole due to the lone pair, but it also had a little boost to the dipole from the NH dipoles that pointed towards N. Because these pointed and added to a dipole that pointed in the same direction as the lone pair dipole, those two vectors add together, giving you a bigger dipole. So the dipole, yes, there is one to the lone pair, but it's smaller than the dipole for NH3. So NCl3 has a small dipole, which makes it bigger than BF3. But because the dipoles all add together in the case of NH3, its dipole's bigger. So if I was to rank in increasing order, BF3 is less than NCl3, who's less than NH3. And I would have had to show all of this when asked to show my work. Okay, well that's it for hybridization, labeled orbital diagrams, and a revisitation of dipole moment. I hope this has been useful. I hope these podcasts are helping you. Let me know what you think of these Scribblecasts. And thank you very much, and I'll see you soon.